Next, we introduce an integration technique called substitution. Let's recall the chain rule for derivatives written for functions h and g. If we define the lowercase f to be the derivative of h and the uppercase f to be its antiderivative, then by simply restating the chain rule, we obtain the following result. Although it looks like a formula, we normally perform it in a sequence of steps, and the procedure itself can be referred to as integration with substitution. For indefinite integrals, we can summarize the procedure in the following way. We first recognize the following pattern, then set up the substitution by setting a new variable, let's say t, equal to g of x, and finding the differential of t. Next, we plug in everything into the original integral, and notice how, because of the discovered pattern, we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function g of x back for t. Let's do an example. We may have to rearrange some terms in the integrand to recognize the pattern. Then we set up the substitution by setting a new variable t equal to 1 plus x squared and finding the differential of t. Next, we plug everything into the original integral and notice how, because of the discovered pattern, we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function 1 plus x squared back for t. For definite integrals, we can summarize the procedure in the following way. We again first recognize the pattern. Then we set up the substitution by setting a new variable, let's say t, equal to g of x and finding the differential of t. Next, we find the indefinite integral as discussed previously, and we finish the process with plugging the original function g of x back for t and evaluating it using the fundamental theorem of calculus. Let's do an example. Again, we rearrange the terms to recognize the pattern, and we set up the substitution by setting a new variable t equal to 1 plus x squared and finding the differential of t. Next, we plug everything into the original integral and find antiderivative. We finish the process by plugging the original function 1 plus x squared back for t and using the fundamental theorem of calculus to evaluate the integral. Alternatively, we can change the limits of integration during the substitution process in the following way. We again first have to recognize the following pattern. Then we set up the substitution by setting a new variable, let's say t, equal to g of x and finding the differential of t. Now, before we continue, we change the limits of integration by applying the function g to the lower and upper limits of the original integral. As a result, we now have a definite integral in terms of variable t, which we find using the fundamental theorem of calculus. Let's do the same example using an alternative approach. We again first recognize the following pattern by rearranging the terms. Then we set up the substitution by setting a new variable t equal to 1 plus x squared and finding the differential of t. Now, before we continue, we change the limits of integration by applying the function 1 plus x squared to the lower limit 0 and the upper limit 1 to get the new lower and upper limits 1 and 2. As a result, we now have a definite integral in terms of variable t, which we find using the fundamental theorem of calculus. The true power of the substitution technique is that it can also be used without any visible patterns. In such a case, we add an extra step of expressing x and dx in terms of t and the derivative of g. Then we plug it into the original integral with the hope that x would cancel one way or another. Whichever x's are still present, we will replace them with the inverse of g. Once we only have t's in the integrand, we continue with the integration process by finding the antiderivative and replacing t with the original function. Let's do an example that doesn't have any special patterns. We set up the substitution by setting t equal to the radical of x minus 1 and finding the differential of t and expressing x and dx in terms of t and the derivative of g. As a result, we have an integral in which some expressions with x get cancelled. But what's left we replace with t squared plus 1. Once we only have t's in the integrand, we continue with the integration process by finding the antiderivative and replacing t with the original function. This technique is especially useful when we integrate a composition of functions in which the inner function is linear. In such a case, we set it up by setting t equal to the inner linear function, and this makes everything just so much simpler to handle. So as a result, we get a simple indefinite integral in terms of t, which we complete by finding the antiderivative and then plugging in the original linear function for t. Let's do an example of a linear substitution. We set up the linear substitution by setting t equal to 3x plus 1 and finding the differential of t and expressing dx in terms of dt. As a result, we have a simple indefinite integral in terms of t. We continue with the integration process by finding the antiderivative and replacing t with the original function. Let's do an example of a linear substitution for a definite integral. We set up the linear substitution by setting t equal to 3x plus 1 and finding the differential of t and expressing dx in terms of dt. Now, before we continue, we change the limits of integration by applying the function 3x plus 1 to the lower limit 0 and the upper limit 1 to get the new lower and upper limits 1 and 4. As a result, we now have a definite integral in terms of variable t, which we find using the fundamental theorem of calculus. We discussed and practiced an integration technique called substitution that can be used for finding definite and indefinite integrals.